The first one is anything to do with proportions. So in math, a proportion means two fractions that are equal to each other. And I'll show you why we would call it that. So, all right, so here's sort of your basic proportion, right? 4/3 equals 20 over x. Now, perhaps it's easy for you to see how to solve this. So the way I usually think of these is that, well, if these things are equal, then whatever I would have to multiply the top by to get from one to the other is the same thing I would have to multiply the bottom by. Since I have to multiply the top by 5, I have to multiply the bottom by 5. So I'm expecting that x will be 15. And it is, right? So that is one perfectly valid way to think of this. And to me, it's the easiest if it works. So I'm thinking I have to do, let's do this times 5, times 5, times 5, right? And so I end up with, I want to do that in black. So I end up with 20 over 15 equals 20 over x. So pretty clearly x equals 15. Right, to me, that's the easiest. It doesn't always line up nicely. So for instance, we could have something like the second one where we have, what do I have to multiply 11 by to get 17? And it's kind of less obvious what to do. It turns out this still works. I would have to multiply it by 17 over 11, but that's not necessarily easily apparent. So what you can do in this situation is cross multiply. Now, I am not in love with cross multiplying. The reason I'm not in love with cross multiplying is because people mix it up with regular multiplying. The only time you cross multiply is when you have two fractions that equal each other. There must be an equal sign in the middle, not times. So in that case, I can say that this times this equals this times this. So I can say 3 times 17 equals 11x. That's cross multiplying. So this is 51 equals 11x. Divide by 11, and you get x is 51 over 11. There you go. That is the only time to cross multiply. Do not try to cross multiply any other time except when you're solving a proportion. That's it. Okay. So here is kind of a classic proportion problem. So I've got two cities on this map that are 3 centimeters apart on the map. And in reality, they are 13.5 miles apart. And so on the same map, 2 other cities are 5 centimeters apart. So how far apart are they in the real world? So what I want to do to set this up is the following. I'm going to say, well, 1, let x equal distance apart in the real world. Apart in real world. In other words, the distance that I'm looking for that I don't already know. So there's a couple ways I can set this up. I can say that 3 centimeters on this map is equivalent to 13.5 miles in reality, and that has to be the same proportion as 5 centimeters on the map and x miles in reality. So that's a perfectly fine way to do it. It'll work out. I think I have a spare page here. You can also do it this other way and say that 3 centimeters on the map is to 5 centimeters on the map as 13.5 miles is to x miles. Both of those will work totally fine. I know I set them up differently, but it turns out that they're both equally correct. So as long as you, the way you want to think of this is this number, this 3 centimeters, has to go with the 13.5 miles in one direction or other, but not diagonally. Whoop, what the heck? That was my combined work problem. Why is this not going the right way? What on earth? Oh, there it is. Okay. Sorry. So this 3 centimeters has to go with the 13.5 miles in one direction or other. Did this erase my what? What happened? I don't know. Has to go with it in one direction or other. Either straight, either up or right, or down or right, not diagonal. And then you solve the proportion. So it actually works either way. This would be 4.5, I think, would be what I have to multiply by to get 13.5. I don't expect that that's obvious. So I'm just going to cross multiply. And we'll say 3x equals 5 times 13.5. 5 times 13.5 is 67.5. So we're going to get 3x equals 67.5. So x is 67.5 over 3, which is 22.5. So that means that the two cities are 22.5 miles apart. The cities are 22.5 miles apart. There you go. Okay, so yeah, I apparently made a bunch of new pages. Let's go back here. Okay. So another classic proportion problem involves similar triangles. These are actually my favorites. I really love these problems. I think because I have sort of an emotional attachment to them when my mom taught these to me when I was really young. Because you can do kind of a cool thing that I will show you in just a second. So the idea of similar triangles is that they are the same shape but different sizes. This is the same thing as saying that they have the same angles. Right, so the same number of arcs means that the angles are the same. So like this angle here is the same as this angle, but the side lengths are different. So we would say these triangles are similar because they're the same shape but different sizes, or you can think of like one is just kind of like a zoomed in version of the other one. In that case, what you have is that the side lengths are proportional to each other, meaning that if x is twice as long as a, then z also has to be twice as long as c, and y has to be twice as long as b, or not twice, right? It could be any number, right? It could be 1.75 times as long and 1.75 times as long. But the ratio of side lengths has to be the same. So if x is 4 and a is 2, well, then that means that z has to be double whatever c is, and y has to be double whatever b is. And so you get this equation where the ratios of the side lengths are just one thing, right? So a over x, that ratio is the same as the b over y ratio and same as the c over z ratio. This turns out to be one of the most useful things in all like physical applications. So similar triangles come up a lot. I'm going to show you a sort of a classic example here. There's a tree that casts a 40-foot long shadow, and at the same time, a yardstick that I didn't spell correctly casts a 2-foot long shadow, and that is enough to tell us how tall the tree is, which seems a little strange, but it's true. So here's how this works. So let's say I've got this tree. I'll draw like a pine tree. Get the art skills here. Yes, the classic tree. And it's casting a shadow that is 40 feet long here. So this is 40 feet. Like that. And so that's where the shadow is. And a yardstick casts a 2-foot shadow at the same time. Now, here's the thing. The sun is coming from the same point. And so these two angles are the same. These are both 90-degree angles here because they're standing straight up. And so that means that since triangles have a fixed 180-degree total of the angles inside them, that these angles have to be the same too. And so that means that what I have here are similar triangles. And this is the exact, oh, that's terrible. This is the exact sort of application where you get similar triangles a lot, is you have like some sort of straight line that's coming at the same angle to two different things. So this is actually a really common application. And so what I want to know is how tall is the tree? So I'm going to call that H. That can be H. So notice that I know everything I need to know except for H. So I can say that the ratio of 3 to H, actually, let's do H over 3. That'll be a little easier. If I do the ratio of H over 3, that has to be the same as the ratio of 40 over 2. Then I solve. Very easy. So 2H equals 120, H equals 60. The tree is 60 feet tall. So you can also do this with mirrors, or a bowl of water actually works really well. If you, well, maybe I won't set that up right now, but because I think you probably want to concentrate on the math. I was going to teach you an experiment, but I don't think we need to work on that. You can probably look up something like that. Just measuring tall things with similar triangles. I bet there's a video somewhere. Anyway, that's the basic idea. You draw your triangles, notice that they are the same shape, and this happens a lot when you get right angles. And then you can use similar triangles to find some missing thing that would be hard to measure, like the height of a 60-foot tall tree, right? That'd be hard to do, to like climb up the tree and drop down a string or whatever. Like, way easier to do it with geometry instead. All right, so that's a classic similar triangles problem. You can find similar, like I would show you more, but there are so many different kinds of similar triangles problems that I could never get all of them. So if you can draw something and you get two triangles that look like they're the same shape, see if you can use similar triangles. All right, so there are kind of two classic rational expressions rather than word problem, or rather than proportions word problems. There's still going to be proportions, but distance rate time problems and combined work, which we'll talk about in a second, which combined work sounds super hard at first, and then you see the trick and it's very easy. So yeah, let me do a distance rate time problem. So I want to show you a couple things with distance rate time. Here's this problem that we're setting up. Yeah, let's read it and then I'll explain what we're going to do. So John, he bikes 10 kilometers to work, and then at lunch, he and his friend Melissa walk 1 kilometer to a sandwich shop. So John's biking speed is 16 kilometers an hour faster than his walking speed. And his total travel time between biking and walking was 45 minutes. So I want to find his walking speed and his biking speed. Now, that's a lot of information to take in. So I want to use a chart to help me organize it. So the chart I want to use is distance equals rate times time chart, which I assume you've seen before, or maybe not the chart exactly, but this equation is probably one that you have seen before. And this is not a hard concept to understand, right? It's all letters, but let's say you're driving 60 miles an hour for 2 hours. How far did you go? Well, you went 120 miles, right? So you were going 60 miles an hour times 2 hours would give you the distance that you traveled. This equation can be solved for any of the variables. So if I divide both sides by time, I get rate equals distance over time. If I divide both sides by rate, I get time equals distance over rate. So all three of those are valid equations that you might want to use. They're all versions of the same thing. Some of them are going to be more, or one of them is probably going to be the one we want in any given case. So here's what I'm going to do. I'm going to set up a chart that looks like this. Distance, rate, time. Bike. And then we're going to have 2 rows, one for his biking and one for his walking. Okay. So what I want to do is the following. I want to fill in what on earth? Where'd my word problem go? Back here. All right, I've done something with my pages that's been weird. Okay. I want to fill in as much as I can. So he bikes 10 kilometers to work, and he walks 1 kilometer to a sandwich shop. Oh, sorry, I see what happened. He bikes 1 kilometer to work, or 10 kilometers to work, and he walks 1 kilometer to the sandwich shop. The thing that I don't know that I'm looking for here is how fast he was going, right? That's the what I want to find. So I want to let R equal John's, let's say, walking rate. So that's going to be R. And then his biking rate, we know, was 16 kilometers per hour faster than that. So this is R plus 16. And we don't know what the time was, but we do know that the total time was 45 minutes. So I made this longer, by the way. I needed a total column. All right, so those are the things that I can fill in. We could write like 11 here and whatever here, but those are not helpful. So here's the idea. So the first thing I want to do is notice that 45 minutes is 3/4 of an hour. And since I gave the biking and walking rates in kilometers per hour, right? The difference is kilometers per hour. I need to change my time into hours. So the 45 minutes is not actually what I want. The thing that I want is 3/4 of an hour. So you got to make your time units consistent, and you have to make all your units consistent. So if distance is given in kilometers in one place and meters in another, you got to make it all the same. Same thing for rate. If it's given in miles per hour and meters per second, you have to convert one to the other. So make sure your units are all consistent with each other. And then what I'm going to do is go back to here and notice that the thing that I'm missing is the time. So time is what I want for my formula. I don't want distances. I don't want this one. I want this one because time is the thing that I'm missing. The one that's alone is the one that we're solving for. Time is distance over rate. Well, I have distance and rate for each of these. So I've got distance and rate for his biking. So his time is distance over rate. And the same thing here. His time is distance over rate. And I know that the total time was 0.75 hours, so I can add up these to get this. That's how these problems go. You got to fill in your chart to help you organize your thoughts, essentially. And I know this is complicated. This always gives people trouble for, I think, pretty obvious reasons. But once you get to this point, it's not that hard. I'm going to have 10 over R plus 16 plus 1 over R is, I'm going to 0.75, I'm going to call it 3 over 4. So we're just using fractions here. And then we're going to solve this equation. So I'm going to find my LCD. I'll need another, well, let's write this here. So my LCD is going to be 4 times R plus 16. And I'm going to take that and multiply it by everything. So we have 4R times R plus 16 times 10 over R plus 16 plus 4R R plus 16 times 1 over R equals 4R times R plus 16 times 3/4. And we're going to cancel stuff like we always do. See what we're left with. So here I've got 40R plus 4 times R plus 16 equals 3R times R plus 16. All right, so let's multiply this all out, combine the like terms, and finish solving. So we got 40R plus 4r plus 64 equals 3r squared plus 48r. What a mess. Let's get it all on one side. I'm going to move it all to the right so the r squared stays positive. So this is 44r plus 64 equals 3r squared. That's a terrible squared plus 48r. We're going to move it all over to the right. So we're going to add 0 equals 3r squared minus 4r plus 4r, minus 64. Okay, so this is a bit of a mess, right? This looks like it's been kind of a pain the whole time, and it has. So let's see what we can do to solve this. I think I see how this factors, but let's see what we can do. That is not a simple factoring job. So let's do the AC method. Actually, let's just do quadratic formula and jam it into a calculator. That sounds like a thing I would prefer to do rather than going through the whole AC method. So let's go here, 3r squared plus 4r minus 64 equals 0. Did I get all those right? Yes. So r is going to be -4 plus or minus the square root of b squared minus 4ac all over 2a. All right, so let's multiply that all out. So this is going to be -4 plus or minus, and of course, this is where the calculator comes in. Do I have a calculator handy? 1 second, let me go check. I think I don't. I'm going to pause for a second. All right, I got Desmos all opened up here, so let's go look at that. So here's what I'm looking at. So we're going to have -4. We'll do them separately. So plus the square root of 16 minus 4 times 3 times -64. And I forgot my parentheses, all over 2a, which was 6. I end up with 4. So that's what I get if I have a plus. Let's copy this thing. That's another advantage here of using a calculator. And we do minus. And that one's negative, so negative doesn't make any sense as far as time goes. So, or as far as speed goes, so it must be this one. It must be 4 for r. So let's go see what that was. So if we recall, come on, r was John's walking speed. So that means that his walking speed is 4, what would we say, kilometers per hour. And so his biking speed is 16 faster than that, so it's got to be 20 kilometers per hour. So this is 4 plus or minus that. So I'm just going to say this. So let's just get rid of this guy. And say that r was 4 or -5 1/3. Now, again, -5 1/3 makes no sense for a walking speed, so that's out. So John's walking speed is 4 kilometers per hour, which is a reasonable walking speed, if perhaps a little slow. And his biking speed was 16 kilometers an hour faster than that, which is, of course, 20. Okay, there was a lot there. Couple things that I want to make sure that we're good on is, number one, you got to make sure your units are consistent. And number two, when you're making your chart, make sure that you put the headers on. People don't put the headers on a lot of the time, which always mystifies me. There's no point to the chart unless you are labeling the headers and labeling the row headers as well. So distance, rate, and time, you have to get these from the problem and then put them in the chart, right? It said that he biked 10 kilometers to work and he walked 1 kilometer with his friend. His biking speed was 16 kilometers an hour faster than his walking speed. And since I don't know either one of those, I'm going to use the same thing that I've said a few times, which is when there's a thing that you don't know, but you need to know it, call it a variable. So we picked one of these. This would have worked just as well, by the way, if we said that his biking speed was R and his walking speed was R minus 16, we'd have gotten the exact same answer. And then whatever thing you weren't able to fill in, like let's say you weren't able to, let's say anything. We weren't able to fill in time, right? Time was blank. So then we had to use the distance equals rate times time formula and then solve that for the thing that we needed. So the thing that we needed was time. That was what we didn't have. So that's what we solve for. And we use time equals distance over rate. And then we use distance over rate to fill in the times. And then once you do that, it's relatively straightforward, because if the time biking and the time walking are these two things, and the total time was 45 minutes or 3/4 of an hour, then you get this equation, right? Once you get to here, you're pretty home free. This is an easy rational equation to solve. This would have been a very simple problem in the previous section or in the previous topic. Well, somewhat simple, right? It's still a little bit messy. But then you solve it, and you solve it just the way we've done it before. So I think the keys here are there's a couple keys here. Number one, when you're making the chart, label everything. Number two, go through the problem slowly and put in the things that are in the problem, put them into the chart as you see them. And number three, whatever's blank is the thing you need to solve for in the distance, rate, time. If the thing you're solving for is distance, that's great. You can just use R times T, and there's usually no rational expressions involved. If the thing that you're missing is either the rate or the time, though, you're going to end up having to solve for those like we did in the previous section, right? Where you get the variable alone that you are looking for. And once you do that, then the equation is usually pretty apparent. Right? Once you've got these things solved for, the equation is usually pretty apparent. It's usually the things that you had to solve for. Right? So we had to solve for time, we had a total time, so we end up with this equation. Then you solve that. So there's a lot of steps to this. Use the chart to help you organize yourself and fill in everything you can until you get some blank spots. And when you get the blank spots, that's what you're solving for. All right, practice these. I've got one on the homework. There's a few more in the further practice that you can try. All right, last one is combined work. Okay, so I've got Claire and Jesus here, and they are painting their house. I hope you can see the word house behind it. The picture, I don't know how that picture shows up properly. Claire could, if she was working alone, she could paint their living room in 4 hours. Jesus, if he was working alone, he could paint it in 3 hours. How long will it take them if they work together? And it's very tempting to look at that and say, oh, well, if one takes 4 hours and one takes 3 hours, then if they're both doing it, it takes 7 hours. No, they actually go faster if they're working together. It's not going to take them longer. It's going to take them less time. And it's not obvious exactly how much faster they would go, right? Because Jesus paints quicker than Claire does, so he's going to get a slightly larger fraction of the room done if they stop at the same time. So it's a little bit weird to think about what to do here. Here is the trick, and it's not exactly a trick, it's just kind of a good idea, which is we need to get them on the same scale, essentially. We don't need to know how many hours it would take them to finish. We need to know how much they get done in and out. So Claire, if it takes her 4 hours working alone, then she gets 1/4 of the job done in 1 hour. And Jesus, if he's working alone, he could finish in 3 hours, so he gets 1/3 of the job done in 1 hour. So here's the idea. If I take 1/4 times the amount of time that they work, so the amount of hours that they work, plus 1/3 times the amount of hours that they work, I'll end up with one finished living room. And that is actually how you solve these. So this is an incredibly easy equation, right? This could not be easier. So we get 1/4 T plus 1/3 T equals one finished living room, where T is the amount of time it would take them working together. And so all we have to do is cancel out the fractions, and we're basically done here, right? So I'm going to multiply everything by 12. We get 3T plus 4T equals 12. 7T equals 12, and T is 12/7. That means that they need 12/7 of an hour. So a little bit more, or a little bit less than 2 hours, which makes perfect sense, right? So if Claire was painting in 4 hours, like let's say Jesus could also paint the room in 4 hours, right? So Claire would finish a quarter of it in 1 hour, and Jesus would finish a quarter of it in 1 hour. And if you're just visualizing a room that's getting filled in, they would finish the whole thing in 2 hours, each of them having finished half the room. Well, it's going to go a little bit faster than that because Jesus works a little bit faster than 1/4 of the room in an hour. So you end up with something that's a little bit smaller than 2, as you'd expect. So that's the idea, is you need to get them on the same time scale, right? You need to know how much they do in 1 hour, not how many hours it takes to finish. So this is your classic combined work problem. And once you see that you want to turn it into rate per hour, this becomes incredibly simple. Like this equation could not be easier. We could literally have solved this on day 1 of this class, right? Day 1 of this course. You'd had no problem. The trick is turning this setup into that. But that is how you want to do it. It's 1 over the number of hours is their rate, and then they're going to do that for some undetermined amount of time. Same thing for Jesus, right? Claire finishes 1/4 of the room per hour times some number of hours. Jesus finishes 1/3 of the room per hour times some number of hours, and that equals one finished room. And you solve for T, and the solving is incredibly easy. And that really is how you do combined work. There really is not much to them once you have seen that trick. Before then, it seems incredibly difficult. But as soon as you realize that the trick is getting them on the same time scale, then the whole thing is relatively easy. All right, that was a lot of types of different problems. I've posted a bunch of links to word problem videos in the module, so check those out. I tried to get a little bit of everything. But I think I will go ahead and stop talking since that's all I want to say. So I will see you guys in the next video when we're starting radicals.